Hello everybody, welcome back to the Gregorius Maths video. Yes, we're carrying on with the Advent calendar, and if I could just... one moment please, let me put on my mic. There we go, okay. Yes, and today's episode of the Advent calendar, if you will, we're going to be considering the following question. If we have... let me write a little bit bigger, based on the previous feedback I've received. If G mod n for some normal subgroup n is isomorphic to H, then if we think about mod as just like division, when can we just times by n on both sides? Does this imply that G is isomorphic to H cross n, direct product with n? Okay, in general this is not true. Take for instance G to be the integers mod 4 and n to be the integers mod 2, then G mod n is not, the integers mod 2, but the integers mod 2 cross the integers mod 2 is not the integers mod 4. So in general this fails, but when does it not fail? And I want to use this as an opportunity to talk about the splitting lemma. So as a disclaimer, what I say in this video applies for abelian groups, with the case of non-abelian groups being, I don't know, a little bit more complicated. So yeah, we're just going to ignore all of the complications and just talk about abelian groups today. Yes, I want to. The main result I want to show is the splitting lemma. Okay, so where am I getting the splitting lemma from? Well, let's begin with this right here. So we have G mod n is equivalent to H. Well, this gives us a short exact sequence. What does it give us? It gives us the short exact sequence from 0 into n, and then we include into G, since it's just a subgroup, and then we go into H, and we go to 0. So why is this exact? Well, the main thing we have to check is that the image of this is the kernel of this. So, well, the image of this is just n, since we are including. And the kernel of this, well, if we think about this, since H is equivalent to G mod n, we can sort of think about this as a quotient map. And, well, the kernel of the quotient map will just be n, which is precisely the image of this map. So we get a short exact sequence here. And the question we want to consider today is, when does this short exact sequence split? And the splitting lemma tells us that the following three conditions are equivalent. So the following conditions are equivalent. So let's just give these maps names. We'll call this F and G. Firstly, G is isomorphic to the direct sum, or direct product, but I'm going to use the direct sum notation just to hint that this generalizes to abelian categories. So G is isomorphic to the direct sum of n and h. That's what we want. And what are the equivalent conditions? i.e., when does this actually hold? This holds when there exists a map called a section, S, which goes from H to G, such that, and I'll draw it on here, S, such that if you do S and then you do G, so basically G compose S, so you go from H to G via S, and then you go from G back to H via G. This is the identity on H. Note that this is not saying that G and H are isomorphic, because this is only a inverse on one side. So that's one condition that is equivalent to this. And the second is very similar. There exists some retraction R from G to N, such that if you do F and then you do R, so i.e. R composed with F, that's just the identity on N. So here are the conditions. So this is when this is true. So that's the answer basically to the question. But of course, if you've clicked on this video, then you're probably the type of guy who wants to know why this is true. So in this video, we're going to show that this condition right here implies this. So we're going to show that if you can find a section, then you're all fine and dandy to go ahead and conclude this. And so, yeah, and the way that we're going to do this is with something called the short 5 lemma. The short 5 lemma says that if we have two short exact sequences and we have maps between the short exact sequences, where the map from the first non-trivial element to the other first non-trivial element, and the map from the third non-trivial element to the other third non-trivial element, if those are both isomorphisms, then the middle map is also an isomorphism. I don't know if that was just word salad, but you'll see what I mean anyway. So, if you understood anything, I don't know how understandable that was, but if you understood anything, you'll notice that, well, we only have one short exact sequence, but we need another. But conveniently, we also don't have this direct sum involved anywhere. So this would be a good time to get him involved. And indeed, what we're going to do is we're going to have our old short exact sequence right here. And then we're going to introduce a very similar short exact sequence, except now in the middle we don't have G, but we have the direct sum of N and H. So this map right here is just the identity. This map right here is just the identity. This is F, this is G. Before I go into this map, because this is the key map right here in the middle here. Before I do that, we should probably define, I don't know, P and Q. These maps right here, because I still haven't shown that this is actually a short exact sequence. Thankfully, it's very easy to do so. Via the maps P of N equals, well, you just send it to N0. And Q of NH, again, very naturally, just gives you H. So this is exactly what you'd expect. And you can check very easily this is a short exact sequence for the middle part here. If you look at the image of P and the kernel of Q, well, if you look at the kernel of Q, you can let N be anything, as you just have to have H as 0, and that's precisely the image of P. So you can see how this is a short exact sequence. And yeah, we're going to go with the section today, so let's throw in this map here as well, this section map S. So we're going to define this map here, phi. And of course, we need to be careful, because if this goes wrong, then, you know, everything goes wrong. So, of course, this is short exact. This is short exact. This is an isomorphism because it's just the identity. This is isomorphism. So the final condition here is commutativity, and so you get the sense that phi needs to. Well, you don't get the sense. You realize that phi needs to commute with everything. So how do we do this? Well, thankfully, for the second component, so for the component, the H component, there's an obvious candidate because we have a map from G to H. And so let's define phi of G equals something, and well, okay, G is a bit, let's say phi of A, okay. The second component we'll just define as being G of A. And notice that this is actually this is actually necessary, because if we want this to commute, then well, we already know what it looks like going here and here. We have G of A, and then we do the identity, so we end up at G of A. And if we go down, we have G of A in the second thing, and then this map just gives you the second thing. So in the second component, we have commutativity, so that's good. The real question is, how are we going to get this involved? And you might notice we haven't used the fact that there's a section here, and this is where we use it. So, notice that because this sequence is exact, we have that the image of f is equal to the kernel of g. So, what we can do is, if we can somehow get a member of the kernel of g, then we have a member of the image of f, and since f is injective by the fact that this is the short exact sequence, if we're already in the image of f, then we can take f inverse. So, how can we get into the kernel of g? Well, that's a good question. What we can do is we can take a minus, so for some element a, minus, well, we want something so that the g of that thing is a. Oh, sorry, yeah, is a. And, well, we know that, so that g of that thing is g of a. But we don't want to just define it trivially, because then it won't commute with everything. So instead, now we can use the fact that we have a section. Indeed, we can use the fact that g composed with s is just the identity. So if we have g of s of g, then that, because of the associativity of composition, that first g composed s will go away and we just get g. So we have, consider an element of the form a minus s of g of a. Okay, now I claim that this is in the kernel of g. And the reason for this is g of a minus, again, I'm just going to use the fact that it's a homomorphism, minus g of s of g of a is equal to, this is the identity. So it's just g of a minus g of a, which is 0. And therefore, a minus s of g of a is in the image of f. And therefore, we're in a good position here. Because f is injective, f defines f defines us a bijection from a to f of a, into the image of a. So once we're in the image, we can define f inverse. So indeed, our thing here will be f inverse of a minus s of g of a. And notice the role of s here. That is what gave us a way to do this, basically. Otherwise we'd be screwed. So this is where the section comes in handy. Now, the final check one should do is to check that this actually now all commutes. So, does this all commute? That's the question. So let's have a look at this first square here. If we do the identity and then we do p, then we're just left with n0. If instead we do f and then we do phi, well, we're left with so phi of f of n is equal to phi of and replace a with f of n everywhere. So f inverse of f of n minus s of g of f of n, comma, g of f of n. But remember, the image of f is equal to the kernel of g. So anywhere we have g composed with f, we have 0. So this is just phi of f inverse of f of n, 0, comma 0, which is just n0. So this square commutes. Excellent. Second square. Again, we have g composed with the identity. That just gives us g of a for some a in g, because I don't want to use g, basically, is why I'm using a. Now, what we need to show is that this square commutes. So if we do phi and then we do q, we get the thing. But this is trivial because, well, if we apply phi to A, we get this thing. But then if we apply q to that, well, we just ignore that and we get g of A. So this square also commutes. And so, what we've shown by the short 5 lemma, everything works. This all commutes. These two maps are isomorphisms because they're just the identity. And the top and the bottom row are short exact sequences. And therefore, we're able to use the short 5 lemma to deduce that phi is a homomorphism. And so we get that G is indeed n cross H, or n, the direct sum of n and H. And so that is a condition in which we can treat abelian groups as fractions, basically. And you can do a very similar thing with this R, and then yeah, that answers the question. I mean, it doesn't show the full splitting lemma because you would need to show that if you have this, then you have this. But it answers the question of, if you have this, when can you get this? And I've shown, because you have this, you get a short exact sequence. And if it splits, meaning if this condition and similarly this condition hold, then you can get this. So, yes, to answer the question, that is these conditions are enough to get this for abelian groups. For non-abelian groups, you have to impose that certain elements commute and stuff. Otherwise, you're stuck with a semi-direct product or whatever. So it's more complicated. But for abelian groups, yes, the splitting lemma, it holds the answer. So yeah, hopefully you enjoyed. And I'll see you tomorrow. I have no idea what I'm going to do tomorrow, but I'll see you then regardless. So, see ya.